Hello, everyone. Welcome to 6-Man. Oli and I are chairing. I think we have enough people to get going. Next slide. This is the note well. You should note it well. Next slide. Administrivia, Chapter Room, you're obviously in the Meet Echo session, I hope. Barbara and Su-Ping are taking minutes. Our thanks to them. Minutes will be available. And there's the link to where the presentations are. I think Meet Echo also has a button that gets you to that. Next slide. So we did something a little different for these sessions. We had two 120-minute sessions and a variety of session requests. So for today, we're doing the new internet drafts and drafts that have had some discussion, but there doesn't seem to be a lot of working group support. The goal is to give time to the speakers to basically make the case for what they are proposing and see if the working group is interested. The second session on Thursday morning, or at least Thursday morning my time, will include the usual introduction and document status. We're getting a report from the spring compression design team, and then working group and active working group drafts. Next slide. And so this is today's agenda. Hopefully all the speakers are here. Next slide. And this is the agenda for Thursday. And so any comments on the agenda bashing? Okay, don't see any. Next slide.
Then we are ready for our first speaker, I believe. Let's see. So Linda, are you here?
Can you hear me?
We can hear you.
Yeah.
Please go
that's
ahead.
Great. That's great. Okay, so this is about IPv6 solution for the 5G edge computing sticky service. We presented this at IETF109, and we got quite a few comments. So we addressed those comments and come back with the update. Next slide, please. Okay, so this is just a brief update, background of the 5G edge computing project. So this is the 3GPP TR2344748. So in that project, it identified many mission critical use cases for local, they call local data network for the 5G core to achieve those edge computing. One of the requirement there is those edge computing services are controlled by their application function controller, and they are using anycast addresses. And you can see here that from 5G core, user traffic is anchored to PSA, PDU session anchor, which is part of the function of the user plane function. And there's always ingress router to the LDN, local data network. And those services, edge computing services, anycast servers are located in the mini data center in very close proximity to the UPF function. There are many of them to achieve the mission critical services. So the assumption is that those services are directly attached and not very far, and there are many of them there. And Anycast is used to address multiple servers. Actually, server to the network perspective actually may be the application layer load balancers. They may have multiple load balancers with multiple servers behind them, but from the network perspective, it's only the load balancer be visible. Next slide, please. Okay, so in that document, it identify many benefits of the Anycast, right? Basically, leverage a network layer to optimize the balancing among different load balancer, and also eliminate the single point of failure at a particular load balancer, and avoid stealth entry in the user device, because some of them don't always query DNS when they change from one location to another location. But it also introduced problems as well, because they are so close in proximity, and so that the routing distance are very small. The differences to different egress router are not very large. The benefit is any of them can serve the service, but you need to stick to a specific ones if you move. And they could have unbalanced distribution, like because UE move frequently, so that even though you plan ahead, you put 3 load balancer attached to 3 routers, because UE move may all anchor towards like particular site, and so causing one site to be overutilized, others being less. On top of that, you could have other issues with more additional servers being added during the operation, during the lifetime of the server. Next page, please. So the sticky service is really about the assumption that not all services need sticky service, only the ones which need the network to optimize. They register with the 3GPP, and the 3GPP recognize those services, and then the network provide additional optimization to distribute among different egress routers. So that's very important part, because we are not doing it for everybody. ACLs are used on the egress router, like R1, R2, and ingress router, RA, RB. So that's very important part. Next page, please. So next page. So using the tunneling to achieve sticky service, what it is when the router, ingress router, RA, based on the running status, distributed from the egress router, and create a tunnel, and to the specific the egress router like R1 be selected. And when the UE move to another location, the router itself will be able to distribute the sticky service ID and the flow ID and sticky egress address to the neighboring ingress router. Those are statically configured. Each router is configured with a set of the routers which are close by, that the service, when they move to anchor to their corresponding PSA, the user traffic should stay together with to the sticky egress. Bear in mind that many of those applications are capable of handling different locations. It's just at application layer, they can actually coordinate and move the session ID at the application layer. But it just takes time, and for some mission critical services, they would like network to help them to achieve better, to stick to the original one to finish the session. Next page, please. So in tunnel service, that the 5G core could coordinate with the ingress router, so that because the session movement, the session control in the 5G core can know that when you move from site A to site B, there's a session control that keep that grace period of transition. It knows where the next UPF is going to. Correspondingly, it can notify the router, telling the router ahead of time that this particular UE is moving from PSA1 to PSA2, corresponding the ingress router RB. So with this, the router A doesn't have to send to multiple ingress routers anymore. It only sends to one the needed information. Next page. So here it is we can either use the destination extension header or the hop-by-hop extension header in the tunnel, so that the traffic, when coming back in the middle of the network, they know where to send it to in the tunnel, and keeping track of the information so that all the intermediate nodes is aware of this particular service has to be sent to the ingress R1. Next page, please. And in the document, we propose this sub-TLV, which we call sticky distance sub-TLV. So with sticky service, we have sticky type, and the sticky type showing that how much this particular service need to stick to the original egress. Some can be strongly need to be stick to, some can be loosely stick to, and then there's most important information is the destination. Basically egress addresses, egress address for the service to be sticked to. Next page, please. So this is mapping to APN. There's a big initiative on the APN for application aware. They propose this application aware ID and application aware service parameter sub-TLVs. So we just map into what they have proposed. So they have an SLA level. Here we have sticky level mapped to the SLA level. They have application ID. Here is the sticky service ID mapped into that particular field. Another one is their user ID, which can be the UE information. And then there's a flow ID. And then the sticky service sub-TLV is mapped into the service parameter sub-TLV. They're just showing how those can be utilized of the APN 6, that document. Over there, they mentioned about using a hop-by-hop count to carry the information, or if the local data network is the SRv6, and how do we carry the information in the SRv6 header. So all that are applicable when we map into those application aware ID. Next page. I think that's it, and we need your feedback, and potentially we think the draft is ready for working group adoption.
So where do you see, I mean, there's clearly work going on in other areas here. Is 6-man the best home for this, or could 6-man review any destination options specified elsewhere, for example? What are the other working groups working on this?
Okay, so we have proposed in several working groups for different aspects. For 6-man is only to identify the next hop option header or destination option header to carry the sticky information. That's what the work to be done at 6-man. At IDR working group is to carry the information from the egress router, like egress router, keep track of all the packets to and from those particular Anycast servers, like load balancer. They also have information about the site capacity. That's because some mini data centers may have higher capacity than others. And you could also carry the information about preference. Like, for example, one mini data center has higher network capacity or more preference than the others. So those information need to be propagated to the ingress router so that the path computation can include not only the round trip delay, because typically today, networking, when we have multiple paths to a destination, we always use our network parameter like distance, routing distance, to determine which one is the optimal one. So with those additional information, the ingress router will be able to combine the routing distance in addition to the capacity or site preference, add it together, apply the combined weight to choose the optimal path. And there's also a proposal in the OSPF extension that allow OSPF to carry those information to the nodes which care about choosing the path based on not only the routing distance but also the weight of the egress.
Yep.
Okay.
Thank
yeah,
you,
we have Fred
Fred.
in the queue. Go ahead, Fred.
Hi there. Yeah, so they have a draft in V6 Ops as well. They will be asking for working group adoption today, and I don't expect it. We discussed this in email. I don't expect to see the working group adopted unless it is conformist to the V6 Ops charter. At the moment, the draft in V6 Ops changes the behavior of IPv6, and you know that's your ball, not mine.
Okay,
Yes, I think our judgment so far has been that we haven't seen much discussion on the mailing list, so we are unsure of the interest in this work. If there is enough and sufficient interest in a working group, I suppose I could use the show hands tool and see what if people have.
I have a question for Linda. So the work that this is related to, like the APN work, has that been adopted in another working group?
No, because we just proposed everything just last IETF 109. So,
Yeah, so
in the IDR, we plan to ask for.
My thinking is that it would be more appropriate to ask 6MAN to adopt this once it's actually a real work item somewhere else, and then it would be reasonable for us to evaluate, the IPv6 extension headers that you're proposing. But I think until that happens, I think it's a little early.
I see. That's a good suggestion. Thank you.
I did start a raise of hand session, so you're if you want to raise your hand or not, there is a session ongoing while we move on to the next presentation. Thanks a lot, Linda.
Thank you.
So, Alexander, I think you're presenting the next session. Please go ahead. Feel free to enable video as well if you want to.
Yes, hello. Do you hear me?
We can hear you.
And I'm sending video as well. Do you see me?
We are.
Okay. Thank you for the opportunity to present. I am going to talk about Slack, stateless address auto configuration, with prefixes of arbitrary length in the PIO. In discussions, we talk about variable Slack. I am the presenter, Alexander Petrescu, and my co-authors are listed on the slide. And this is IETF 110 in March 2021. Next slide, please. The contents of the presentation, I will mention only 2 points that are described in this draft. In the introduction, a little bit of the problem statement for vSlack, and the one slide on the implementation of vSlack. But in the draft, there are more topics that have been given equal importance. I'm listing them bullet by bullet. The history, what we understand, the history behind the 64-bit fixed boundary, some statements about identifier and subnet length. Third bullet, recommendations for implementations of VSLAC. Then recommended use cases where 64-bit prefixes, not VSLAC, should be utilized, a large majority of cases. Then what are the reasons for longer than 64-bit prefix length? And then using greater than 64 prefixes by ISP is normally strictly prohibited, so we don't have a race to the bottom problem. A brief comparison between static SLAC, DHCPv6, and VSLAC, and then again some variable SLAC use cases. And then I will go now to describe some points of the problem statement. Next slide, please. Well, there are very many aspects of this problem. We selected only a few of them that I try to illustrate with a figure in the center of the slide and the bullet points in the right part of the slide. In the center of the slide, in the upper part, you see in the figure the internet and a GGSN, which is part of the 3GPP network, and that advertises a 64 prefix to the UE, which is the user equipment. Then this user equipment needs to extend the network beyond this just 164. So it could try to make a 65 prefix or even a 66 for the subnets behind the user equipment. Such use cases are, for example, a mobile hotspot, a subnet in an automobile or other mobile platforms. Now, in the text part on the right-hand side, I listed texts about what are the problems in doing that. First and foremost, in the IPv6 addressing architecture, RFC 4291, all the addresses currently allocated, which are 2000:/3, cannot have other than 64-bit interface identifiers. The second bullet is that all mobile phone operators allocate 164 prefix for one user equipment. Third bullet says that the DHCPv6 prefix delegation is blocked by a majority, if not all, modems of the mobile equipment. It is also impossible in implementation to use SLAC with a prefix of length 65 in the router advertisement. For example, in Linux, this is not working simply. This makes that the problem is that it is impossible to extend the network to multiple subnets beyond the user equipment. For further description of the problem, we refer to this draft Mishra v6 variable SLAC problem statement that is pasted at the bottom of the slide. Now I'm going to talk a little bit about the implementation that we wrote and that we propose in this draft. Next slide, please. The implementation that we wrote, I thank actually to Dmitro Shiti, our co-author, for this writing that he took several months to make it, to progress it. In Linux, it is just a local parameter, a ccTL. The default value of this parameter is 0, which means that SLAC acts as before, uses 64-bit IIDs and prefix lengths. But if an operator sets this value to 1, it makes that prefixes of length other than 64 are accepted for SLAC. For example, a host that receives a 63 in an array will form an interface ID of length 65 and subsequently an address of length 128-bit. This implementation is a patch freely available on GitHub. And we have also submitted for consideration to Linux maintainers, but we have some feedback from them asking the status of this proposal that we have here at IETF. In OpenBSD, we have learned that there is an implementation of RFC 7217 that works okay with variable length plens in SLAC. And in FreeBSD, this is not the variable slack is not working. Only 64-bit IDs are implemented, respecting the standards. And we have submitted what we think to be a bug report, and we complain about this 64-bit limit in that. So that is the implementation that I was trying to present. And at this point, I might wonder if there are any comments. Otherwise, I have an additional slide on what we discussed, not publicly, but privately with a few people about the potential next steps. But if there are any comments here, I'm interested to, we authors are interested to hear these comments.
Jen, go ahead.
First of all, I have a deja vu, right? I think we've been in that discussion a couple of times, but I have like two questions. First of all, why are you calling BSD behavior a bug? My understanding is we're all here to discuss how operating systems should behave, and after we agree on something, that should be implemented. If operating systems started to do something which is currently prohibited by RFCs, I would not call it a bug, right? If they start doing this, like we all can go home and just forget about making any standards because operating system would do whatever they want. And I'm also a bit confused about the draft. I read it, and in the beginning of it, the draft is saying, we want to do prefixes which are shorter than /64, and we go and explain why. And yes, we also allow longer prefixes, but operators should not do this now. And then all use cases I found in the document talking about longer prefixes, and I could not find any compelling use case for shorter ones. So I'm not sure why we need this, especially providing that I'm quite sure that operators would not listen, right? They're only doing /64 now because they could not do longer. As long as we allow them to do longer, it would be the race for the bottom. And our you should not do this would not work. So I'm still not convinced we are not opening the door to the race to the bottom by doing this.
Yes, if I can reply at this point. On the calling it a bug report, I think it is because the tool of submitting proposals of improvements is called a bug reporting tool, if I remember correctly. But okay, probably bug is should not be used, but we could also see it as a suggestion for a new functionality that could also be a experimental functionality, if you wish, into which some things are tried, but by default they should be off. Of course. Then with respect to the question of these shorter and longer prefixes, okay? Now, basically, I agree with you that if vSlack allows for longer prefixes, then operators might be tempted to allocate longer prefixes to the end users. And that could create a race to the bottom problem, and that is not good and should be avoided. There should be something, some tool, some mechanism, I don't know, that should not allow for this to happen. I don't know what. But now for shorter than 64, shorter than 64 prefixes, then that could be a good idea. And if the operator advertises a shorter than 64 prefix to the end user, then the end user would still need to form a 65-bit interface ID, which is the interface ID is longer than 64. That is what we tried to express. Maybe we could clarify it. And then the third point that to answer this is that if this document does not progress or is outright rejected, not even as experimental accepted, or if this is completely stopped, then in the implementation, I must say that I will be again tempted to use this 66 prefixes inside the extended network, because the operators will always allocate a 64, and then the only thing one could be tempted to do is to create 66 out of this. So that is a conditional. I'm not sure I answer whether we could discuss further about this, but I agree with most points that you raised, Jen, and the draft could be further clarified on these points. And the slide could be improved to remove this bug word. Yeah.
Any more comments? Do you want to show your last slide, Alexander?
Yeah, please, last slide, please. If I think I still have 5 more minutes. We brainstormed with a few people, and a few suggestions were made, but it's nothing private about this. But I really trying to push this forward, but I'm not clear how to proceed and how to. So one of the points that was listed is to make a liaison between IETF and 3GPP and maybe make the most of this work at 3GPP, such that make a requirement at 3GPP to advertise shorter than 64 prefixes to the user equipment. That's a possibility. A second bullet says that we could link the vSLAC concept to the GTP, generic tunnel encapsulation protocol. I think that is a 3GPP protocol. So these two concepts could work together. A third bullet suggests that maybe we could ask IANA for a sub-range of this 1FFE/3 space, all these addresses that start with 000 binary, which is not subject to the 64-bit boundary. And this could be performed on an experimental kind of activity into which not only vSLAC could be used, but maybe other drafts and maybe a little bit of longer prefixes, but smaller space in this that could be allocated. That again, fourth bullet is to make vSLAC on an experimental status was suggested. Fifth bullet is an activity that was started at the earlier IETF on a 64 share V2. Cameron Byrne, I think, proposed it, but it's not an internet draft. And maybe it could be possible to take that text, put it in a real internet draft and submit it to IETF. Then the next bullet, make a lightweight prefix delegation mechanism for ND and NDPD. I'm not sure whether somebody has already worked, and this is basically a question I have to people present in the room, if somebody already worked on this NDPD lightweight prefix delegation. Next bullet is to use a method like in draft Naveen, into which a host puts a specific request in RS, router solicitation, to request multiple 64 prefixes, or a non-64 prefix maybe. That's another protocol proposal. And then I know that Pascal Kubert has a activity proposal for IP over wireless, and since this happens on a wireless link, maybe bring vSLAC there. And also Edward proposes an activity or a sort of concept on next generation Slack. And maybe vSLAC could be part of that next generation Slack. That's another potential next step. And then again, somebody also proposes, is there another way possible for this to proceed? Is there another, because the problem is still there. All mobile operators allocate a 64 to a user equipment, and many user equipments need to extend beyond. So that is my last slide. Yeah, I hope I managed it. Well, I'm all ears now. I listen.
You seem to be missing, at least in HomeNet. This was also discussed, many years ago, and the solution they at least implemented was just to use DHCP, which supports other prefix lengths just fine. At least there you have a solution that is widely implemented and supported in all equipment.
Yes, noted. There is HomeNet, probably others, and I will now. It would HomeNet protocols are normally for home networks, in-house networks.
Sorry, I didn't at all suggest the HomeNet protocols, I suggested that they also discussed this exact same problem, and the solution they chose was a solution that has been standardized for many, many years, which is just to use DHCP for address assignment. Then you don't need to care about the 64-bit boundary. You can make as small allocation links as you like without any changes to either implementation or standards.
Yeah. Maybe HomeNet protocols, standardized HomeNet protocols, DHCP, maybe in home they are not blocked by manufacturers of chips in home.
You don't need to run this across the 3GPP link, right? This is all you're proposing here is inside of the network, right? So if you just don't use Slack, you can use the DHCP for address assignment instead inside of the site, and this will be will not require any changes.
Yeah. Okay,
there might be, some.
Yeah. We have Lorenzo in the queue. Why don't you go ahead?
Yeah, so I actually had a question about the modems, the modem vendors blocking DHCP-PD. I mean, I think that seems like, do you have data on why they do this? Because I mean, it's not sort of written in any standard that they should do this, and in fact, the 3GPP release 10 standards do support release 10 and above, and now we're on release 15 or 16. They do support DHCP, so DHCP-PD. It's a supported part of 3GPP. So the other thing is, given that, I'm not sure that, there's actually a problem to solve here. If your primary use case is to be able to assign a shorter than 64 prefix to a mobile node, that's already supported by the 3GPP standards. It's just a deployment problem. And writing a new draft is unlikely to affect the reasons why it is or is not deployed.
Yes, so with respect to why some or most mobile modem manufacturers block DHCP v6, because that is what they block. They don't block in particular the PD part of but DHCP v6. Blocking DHCP v6 means blocking the port numbers of DHCP v6 or blocking the multicast part of DHCP v6. These are the two things that are blocked by various men. Now, why they do that? We have a list of reasons why they do. I mean, we speculate why they do. We don't know exactly why. And even some people at the modem manufacturers make some statements that are backed more or less by some. So there is a list of reasons. One of them that it might be a heavy operation to do DHCP as opposed to doing Slack. The other is that it constitutes any open port is a security hole, and multiplied by the number of smartphone devices sold, it amplifies a lot this security risk. Another is that these modem manufacturers have heard from IETF and from others, which is an old wisdom at IETF, that in IPv6, the way to configure addresses is Slack and not DHCP. So that's an old wisdom, but it still persists in many circles. And I think these are the main reasons that I have heard about, but that is the way it is. That is the way it is in practice. And probably new releases will change things, but it is now several years that operators allocate only 64s to end users. I forgot the second question. Yeah. Lorenzo.
If this is just a deployment problem, right? If the operators want to use DHCP-PD or anything else really that's there for them to use right now, writing another draft or another standard is not going to affect that, right? I think. Yeah.
It is true. It is also suggested to make this more of a 3GPP document or a requirement at 3GPP. And my reply to that is that sometimes 3GPP does refer to internet drafts when writing their own requirements. And so that is probably a possibility. I mean, yeah, we could try to do that rather than pushing this forever at at IETF. And yeah, it's a good suggestion that we take into account. We will also look into that 3GPP matter. Yeah.
Yeah. Well, super.
Right.
Thank
We are
you.
out of time. Thank you.
So then we have our next presentation, Associated Channel over IPv6 with Fan Yang. You are presenting, right? Please go ahead.
Can you hear me?
We can hear you fine.
Oh, okay, good, because it shows there is some error there. Okay, thank you, Chair. And this is a very new draft. It's the 00 version draft. And in this draft, we introduce an associated channel over IPv6. And this, for short, we name this associated channel as ACH, and the current scope is IPv6 networks. Next page, please. Yeah, the higher level motivation is we see that from IPv6, IPv4 to MPLS, and from MPLS to IPv6. And currently nowadays, the IPv6 provide connectivity in many new emerging and also the legacy networks. And in all these scenarios, actually the IP services require the higher quality of the RSA guarantee, and rather than the best effort. And we see the segment routing over IPv6 provides optimized route for service forwarding via the routing programming on SRH. And we introduced this ACH and to provide the control and management programming capabilities to the service forwarding. Yeah, next, please. And later on, we will have some examples to show the applicability. Yes. And the ACH architecture, and the cloud in the middle is it is an IP network, and there is a black line between the first node and the fourth node, and it represents it is an IP path, and user data is transmitted in the along the IP path in the yellow arrow, and these blue arrows are the associated channel created to the IP path, and it is if you look at one arrow, it is a control channel, and this associate channel is associated to IP forwarding path and carrying the messages of the control and management protocols, and aiming to provide the control and management functions. And if you look at the right bottom graph there, and it shows where the ACH in one network node, and the control and management planes generate the control and management messages and carried it in the associated channel and transmitted in the data plane. Yeah, next page, please. Yes, in the draft, we define the ACH as a TLV format, and the first type specified it is a control channel for one specific IP path, and the channel type specifies the type of the control or management protocols. To identify the IP path and also associate the IP path to the ACH, the associated channel ID is identified there. Is defined there, and the control and management messages can be carried in the fixed messages in the value field. And this ACH flag. It is a ACH TLV, so this TLV can be flexible, encapsulated in the IPv6 extension headers, including the DOH, hop by hop, or SRH. It can also be encapsulated as payload in a systatic packet. And I will use the following examples to show the application, the end-to-end application, hop-by-hop applications. Next page, please. Yeah, we identified our, we give just two examples. One is the, we call it, we use it for the unified OEM. Here we give three protocols, we list three protocols that used for the OEM functions. And we also identifies this several problems that this protocols, with these protocols. For example, these protocols are designed to perform different functions, different OEM functions, but they also have overlapped functions, and they use different session identifiers, and also deeply encapsulated in the IP packet. And if there's and because they are defined as an end-to-end session, so the intermediate node is not aware by the end-to-end session. So we try to come up with a simple solution to carry these OEM messages in the ACH, because ACH is a TLV encapsulated in IP layer. So all these OEM messages are encapsulated in pure IP layer, and it reduces the number of protocols sessions and also unify the session identifiers. Yeah, the figure below shows that the example is that if we encapsulated delay measurement ACH TLV inside the IPv6, actually I should use the DOH header. And this ACH TLV is encapsulated in the IP layer and transmitted from R1 to R4. When R4 receive it, it will process the ACH TLV as it, since it is the last, it is the destination of the IP path. And when it receives the ACH TLV, it processes the TLV and measure the delay. Next page, please. Yeah, the second case, it is more complicated, but it's very easy to understand. Actually, there are two associate channels used here, and the first one is R1 generated this fault management probe, and to R4, and this fault management ACH TLV is encapsulated in the IPv6 hop-by-hop extension header, so that each node will process this TLV, and if for example, if R3 detect there is a signal degradation on the link, and it can simply set the flag when it processes the TLV and indicate the arrow to the following node. And when R4 receives this indication, and it generates another protection switch request to R1 to ask R1 to switch the forwarding path, but this message is using another. This message is using another associate channel, and on this associate channel, it is end-to-end. The ACH TLV is encapsulated in the DOH header, because it is a message sent from end to end to tell R1 there is not to tell R1 the request of the switch. And you can see they use different associate channel and with different associate channel ID, and also specify the different channel type. Yes, next please. And we yes, actually so far we have already received a lot of comments and suggestions about this draft. So we would like to have more discussion on this topic and to refine this ACH, how it used in IPv6 network. And maybe since segment routing SRv6 is a specific type of IPv6, we may also want to specify maybe specify the how ACH used how ACH used over SRv6 maybe in another draft. And we also see there are different, depending on the applications, that the ACH can be used in different ways. So we'd better to separate the draft to specify the application used in ACH. Yeah, and I also want to say that actually ACH is not, maybe I have two examples here, but ACH is not designed only for OEM. We would like to have it to have ACH to carry the control and management messages for different use applications. Yes,
Okay.
and that's it. Thank you.
Why don't we see if there's any questions from the working group? I have a few, but
yeah, I also have this discussion with I think in other I'm not maybe
okay, well,
privately. I'm not sure. Sorry.
Is there
Yeah,
anyone
also
who has any questions?
yeah, actually we want to present this. Go ahead.
Eric?
Well, yeah, I wanted to ask about the relationship to other IOAM work. I know there's some stuff in IPPM and other things.
Yeah, actually, if you ask me the relation between the ACH and IOAM, I think IOM was one of the case that can make use of the can be one of the type of ACH. And I think the big difference is IOM is only designed for the OEM, but if you just look at the encapsulation, maybe they are similar, but the design background, the design behind these two technology are different, because we see there are so many control and management messages. There are requirements to carry this control and management messages on the IP layer if we don't have segment routing, but we don't have some of them. They don't have any signaling protocol to carry them. So ACH is designed, is open to it's open to any applications that if you think that it should be used in the IP layer. To sum up, I think IOM is one of the type of ACH. Currently, I don't have it in the draft, but I have some something in mind to use ACH in other application. But yeah, it's just under the discussion. So maybe in future that we can have more application use cases there.
Yeah. So how does this relate to other things like APN?
I'm not sure that I don't have this on mind. So currently, from my side, it's not so related to APN. Yeah.
Okay. And this is just traffic between routers, so the packets are created by the routers. This is not inserting this in data packets.
No, I think it's limited to the network nodes. Currently, we don't want to have this app capability from between the hosts.
Okay, thank you. All right, I think we are about out of time, so thank you. Or I guess you have another talk.
Yeah, thank you.
Please go ahead.
Yeah. Actually, this topic includes two drafts. One is the draft named segment routing for redundancy protection in Spring Working Group, and the second is this one is the SRH extension for this redundancy protection. And yeah, I will give this the introduction for both of them. Yeah, next please. And just a short introduction to this redundancy protection, what it is. So actually, the service protection comes from one of the three techniques defined in deterministic networking in the DEN networking group. And also we see there are also requirements for providing strict end-to-end reliability to the services. So here that we have this redundancy protection, it is one of the mechanisms to achieve the service protection, and it follows the principle of pre-auth, and that stands for the packet replication, elimination, and ordering function. That we have example scenario, very simple example scenarios there, and when there is when the flow arrives, and we name this the red is the redundancy node, and the MER is the merging node, and when there is a flow comes to the redundancy node, and the flow is replicated to two copies, and these two copies will go through different paths to the merging node. The first one will go to the will go from redundancy node to R3 to merging node, and the second is to R4 to merging node. And the first received packet with the sequence number, with the same sequence number packet, the first packet with the same sequence number will be transmitted from merging node to R2, and the other one, the redundant packet, will be dropped. So that in this way, that to protect this redundant path, to protect there is no packet loss, to protect the service without the packet loss. Yes, next please. Yeah, to support the redundancy protection, actually we defined four information, and first is the redundancy segment. It performs the packet replication function on the redundancy node, and it's associated with a redundancy policy. Actually, is a variant of the SR policy, and in case of the SRv6, that we define a new behavior and R. The second piece of information, second information is the merging segment, and is similar to the redundancy segment. It performs the packet elimination on the merging node, and a new behavior and M is defined. And to identify the unique flow and identify the packet sequence within one flow, that we define the flow identification and sequence number there. And in this draft, we extend the SRH optional TLV to encapsulate them. And the last information is we define this redundancy policy. Actually, is a variant of SR policy. The difference is we have more than one ordered list of segments, and all these ordered list of segments are used at the same time. That's the difference from normal SR policy. And the blue and the test in blue is what we have for in the draft in this working group. Next, please. Yeah, here we take SRv6 as an example to show the redundancy protection process. actually here we have two different two choices to deploy this this process. The difference is depending on where do you want to assign the flow ID and generate the sequence number. And the first choice is to use you assign the flow ID to the ingress node of the SRv6 domain and generated the sequence number there. And the second choice is you assign the flow ID to the redundancy node, and also the sequence number will be generated there. And the difference between these two choices is the first one that you have the flow ID and the sequence number causing the path all over the SRv6 path, forwarding path. And the second choice is that you have this two information only between the redundancy node and the merging node. I want to explain all these headers, but let's just focus on the TLV in the orange color in orange, and this will identify the flow identification, the sequence number, and we capsulated in the TLV that in the IPv6 SRH header, and this information is carried to the merging node. Actually, this information is only meaningful for the merging node when it's perform the elimination, and yeah, and also let me think if I miss anything. And yeah, by using this information, and it's forward the packet and also drop the redundancy packet, but that is defined. That is the behavior definition that defined in the merging node, in the merging segment. So yeah, I think that is what I want to explain here. That there are two different choices, but no matter which choice, this information will be encapsulated in the IPv6 header, where the merging node process the merging segment. So it always they are always encapsulated together in one IPv6 header. Yeah. Next, please. Yeah, and here a very simple TLV defined to carry these two information, and I also see there are discussions in the mailing list to discuss that the IPv6 flow label can be used to identify the flow ID. So I think I would like to have more discussion there. Yeah, currently I don't have any strong preference to have it in a TLV or in the IPv6 flow identification flow label, but I think it also be affected by the choice that we made from last slide. If we want to use it only between the redundancy node and the merging node, I think that it's okay to use it as the IPv6 flow label. But if you want to use it, if you want to have the flow identification from the ingress of the SRv6 domain, that means that you will have this flow label will be used for ECMP and also used for the for this redundancy protection. So that will be some conflict there, I think. Yeah, next, please.
Oh, never mind. So is that the same flow label as in the IPv6 header or something different?
Yeah. I mentioned this IPv6 header flow label. Yeah, because people think that there's some discussion that they think the flow identification can be carried in the IPv6 flow label in the IPv6 header.
So is that a yes or no answer?
Yeah, if I have a preference, I think I prefer to use it here in the SRH optional TLV, because I see if you use it, I've already mentioned if you use it in the IPv6 header, that will, and this information is encapsulated at the ingress node. I mean, the IPv6 flow label can only be used for this function, but not for the ECMP, like ECMP in other part of the forwarding path.
Okay, so we have two people in the queue, Eric and then Darren. So Eric, why don't you go ahead?
Yeah, thank you. I have a multi-part question. So my scan of the document is that you want to allocate some new TLVs from within the segment routing header?
Yeah.
And the IANA registry for that looks like it's IETF review, which means, which means this doesn't have to be done in 6-man. So this could be done by Spring or it could be to somewhere else. I don't know. I'll leave it to you and the chairs in the group to decide if it belongs in 6-man, but I'll just observe that I think it doesn't have to be done here in order to get your IANA allocation. So.
Oh, okay. I'm not aware of this, so I don't intentionally to put it in 6-man. I thought it should be there, but if not, that we can also move it to Spring Working Group, because we also have this mechanism defined there. Yeah.
Yeah.
Yeah, I think I will leave this to the working group chairs.
Yeah, Darren?
Make the same comment as Eric on where this could live, but since that's already made, I just wanted to make a comment on the flow label. If you do want to move this flow ID into the flow label, load balancing nodes are supposed to take into account more than just the flow label when they determine how they're going to be performing ECMP or UCMP load balancing. So if you're concerned that you may not have as much variability in that flow label, if it's equal to what you're specifying as a flow ID, that concern may not be all that great.
Yeah, I think I agree with you. Yeah,
okay.
Yeah. The ECMP, UCMP is it should be protected from this. It should be used. It should be. They should have this capability to use it. Yeah.
Yeah. So I would add that if this is, to the other point, if this is just wanting to define a TLV for SRH, then I think having that work in Spring would be at least fine with me. I'm not sure there's anything particularly IPv6 thing that 6-man, I mean, it might be good for 6-man to follow it, but I think Spring could definitely own it. It's more relevant to the work that's being done there. Stuart?
Of course, all the work on pre-off is happening in DETnet. I would have thought that this belonged over there, where there was a large body of people interested in building reliable streams.
Yeah, actually, we have this history that we first proposed this in DETnet, and after a few meetings, they proposed that we should, because this include the implementation. No, it includes the segment definition and also this how to encapsulate this metadata, and also include the SRV the SR policy definition. So they shift this work from DETnet to Spring, and if the chairs agree that we can have this IANA allocation in Spring Working Group, I think we can just focus on the Spring Working Group, and then after it's all done, and we come back to DETnet if it is necessary. Yeah, actually, this work proposed like 2 years ago to DETnet first.
Making any changes to the data plane, but this is a function that DETnet needs, in my view.
Yeah. Yes. DETnet need it, but they need the extension on SRv6, so we shift the work to to Spring. Yeah.
All right. Any other questions? Okay, good. Yes, I think the conclusion is that probably 6-man is not the best place to own this work, and it could be Spring or DetNet or somewhere else. Thank
it's
you.
often useful to use the working group that has the need for it to define it and get review from the other working groups, you know, Spring and perhaps even 6-man in this case. So, but we can take that offline.
Yeah.
Okay, so our next presentation, Omni Adaption Layer. Fred, the floor is yours. Fred Templin, are you there?
There we go. Hi, Fred. Go ahead.
You hear me okay?
We can hear you okay.
Okay. This presentation is on the Omni adaptation layer. Go to the next chart, please. So this is based on what's known as the Overlay Multi-Link Network Interface, the Omni interface. And you can see the draft name there. What it is an overlay interface configured over multiple underlying interfaces. And if you look at the diagram on the left, that's from RFC 5558 from back in 2010. You can see that thing called the VET interface is that side-looking thing that is got some substance over underlying interfaces. And then later in 2016 in RFC 7847, a better diagram was drawn. And you can see the Omni interface there is at a layer below IP, but above the underlying data link interfaces. That's the diagram that we're using from now on, is the 7847 diagram. Next chart, please. So what about the Omni interface characteristics? It's an ordinary IP interface with a 9180 MTU. And what that means is that the IP layer expects the interface to deliver packets or fragments up to 9180 bytes. Internally, the interface performs IP encapsulation to convey original IP packets up to 9180 bytes over the diverse underlying interfaces. Well, we've got some things to think about though, because the underlying network path MTUs are often much smaller than 9180. For example, the IPv6 minimum path MTU is 1280, and there's no in the network fragmentation allowed in the IPv6 paths. IPv4 minimum path MTU is only 576, and the reason for that is because the minimum IPv4 interface MTU is 68 bytes, but the network can fragment and all destinations are required to assemble at least 576. So what the Omni interface needs to do is to adapt the Omni interface MTU to the underlying network path MTUs. And for that purpose, we have what's known as the Omni adaptation layer, or the OAL. Next chart, please. So what the OAL is an Omni interface sublayer below the IP layer, but above the underlying interfaces. And it's based on RFC 2473 encapsulation, IPv6 encapsulation, in other words. When the IP layer delivers a packet to the Omni interface, remember it can be up to 9180 bytes, the OAL inserts an RFC 2473 encapsulation header and appends a 2-byte trailing Fletcher checksum to form the OAL packet. We count the trailer as part of the payload at this point when we put the payload length in the OAL header. The OAL next then uses IPv6 fragmentation to break the OAL packet into fragments containing no more than the maximum payload size. So there you see the fragments, and each one of them has a payload in blue that is a portion of the original IP packet that is no larger than the MPS. And the final fragment has that little trailing checksum attached to it. Next chart, please. So then what happens next is that the OAL source encapsulates each OAL fragment in underlying network headers, for example, UDP IP if we're sending over the internet, and then sends the packets over the underlying interface. So there you see the fragments from before, but they have these little green U1, U2, U3 headers on them, which is the underlying network headers. And what's good about these things is that they will get across any network path because we've taken care to be sure that the maximum payload size is going to be small enough to fit into any path MTUs, regardless of what interfaces there might be in the path. And when the fragments get to the OAL destination, it discards the underlying network headers, reassembles the OAL packet and verifies the checksum, and then discards the OAL header and trailer and delivers the original packet to the IP layer. Next chart, please. So how do we find out about this maximum payload size? So some hops in IPv6 OAL destination paths could be over tunnels over IPv4, through IPv6 over IPv4 translators, etc. And the packets could also be asked to traverse multiple concatenated internetworks with diverse IP protocol versions, and I'll talk more about that later. The IPv4 minimum path MTU of 576 is therefore assumed unless there's better knowledge. So now let's look at some worst case analysis. For the OAL encapsulation header, we have 40 bytes for the RFC 2473 header, plus 40 bytes for an OAL routing header, a single routing header, plus 8 bytes for the fragment header. So 88 bytes for OAL encapsulation. And then each underlying network, the worst case we have would be a 40 byte IPv6 header or a 20 byte IPv4 header, plus 40 bytes for security encapsulations such as IPv6, SSL, TLS, etc., plus an 8 byte UDP header. And therefore, we know that the minimum maximum payload size is 576 minus 88 minus 88 equals 400 bytes. That means that in the worst case, we can expect that if we limit our payload size to 400 bytes, these fragments will get through any path anywhere in the network. So for an example, if we had a 1500 byte original IP packet, that would take up 4 OAL fragments, 3 fragments with 400 byte payloads, and the final fragment with 302 byte payload, which includes the 2 octet trailer. But fortunately, larger per path maximum payload size values can often be determined so that we don't have to have all of this overhead and all of these fragments. Next chart, please. So the OAL source can set path maximum payload size values that are larger than the minimum maximum payload size for specific OAL destinations. So if the OAL source knows without probing that the path can transit a larger MPS without loss, it can set that larger value for that OAL destination. Otherwise, the OAL source can send probes to the OAL destination to discover larger path MPS values. And that probing would be in the standard of RFC 4821 or RFC 8899, which is MTU probing. The OAL encapsulation is not needed when the source and destination are on the same link and the original IP packet fits within the link MTU. So the game here is you want to send with as few encapsulations as possible, preferably with no encapsulations. And that's a case in which you can get away without even have to have the 2473 header. Next chart, please. Okay, so by using the minimum maximum payload size, we have a safe assumption that works over all paths, and non-final OAL fragments must contain at least this much worth of payload, so we wouldn't have any tiny fragments. The only OAL extension headers that can be included are 1 fragment header and 1 ORH, but no other IPv6 extension headers. And that allows OAL destinations to drop any non-final fragments less than minimum maximum payload size of payload, which defeats the tiny fragment attacks. And OAL destinations drop OAL packets and fragments with OAL extension headers other than a single fragment header and a single omni routing header. Next chart. So since we're inserting an RFC 2473 header, we need to have IPv6 source and destination addresses to put inside of it. And for that, we use RFC 4193 unique local addresses with the FD :/8 as the source and destination to enable forwarding at a layer below IP. So from the perspective of the inner IP layer, be it IPv6 or IPv4 or some other IP version, the OAL forwarding would be indistinguishable from layer 2 bridging. And that means that we can use it to traverse multiple independent internetworks that are concatenated by bridges. Next chart. So here's what it looks like in a single network traversal. We have an original source that sends an original IP packet that traverses some edge network until it gets to a node that has one of these Omni interfaces. So you can see the diagram on the left there with the Omni interface. And that Omni interface then performs OAL packetization and then breaks the OAL packet into encapsulated fragments that you see down by the blue cloud there. Those fragments are guaranteed to get through that blue cloud and get to the OAL destination, which reassembles and then removes the encapsulation headers and forwards the original packet to the final destination. Next chart. So what happens if we have multiple networks that we want to traverse? We have the original source sends to the first blue network, and there's an intermediate node between the blue and the red networks that has an Omni interface, and it performs. I'm sorry, is my audio visible? I'm getting a signal that there's some errors.
Yeah, same thing happened to me. It seems to be back now. We can hear you, Fred.
Okay. So then the second intermediate node concatenates the red and the yellow networks together at a layer below IP, and then the packet finally pops out to the final destination where the Omni interface nearest the final destination removes the encapsulations and forwards the original IP packet to the final destination. Next chart, please. So this Omni encapsulation lets us do some interesting things. We can create what's called a super packet. And Omni original IP packets that are smaller than the Omni interface MTU and arrive in bursts can be concatenated together into a single packet.
Fred, you have about 5 more minutes.
Okay, I'll try to move faster then. So it may be more efficient to pack multiple original packets into a single OAL super packet. As you can see here, we've got multiple IP packets in a single OAL header and checksum trailer. Next chart, please. OAL packet size feedback. Although the interface accommodates packets up to 9180, it's not always good to continuously send such large packets. Classical path MTU discovery sends back a packet too big hard errors to inform the sources of packet loss due to size restrictions. But the Omni interface supports continuous forwarding of packets up to 9180 bytes while sending packet too big soft errors. And what this results in is lossless path MTU discovery, which is kind of like a holy grail thing that we've been searching for really decades, and a way to do this. It's a new capability for hosts to dynamically tune packet sizes for optimal performance without loss. Next chart. OAL is a new sublayer, so it has to include its own integrity check. It uses Fletcher because it's dissimilar from the underlying interface CRC32 and the upper layer internet checksum. Underlying networks can disable UDP checksums if possible, because we've got the OAL checksum. And some underlying network hops might not include integrity checks at all. So in that way, the OAL checksum actually improves the integrity of the internet over the current state of affairs. And Bob, if I could very quickly jump to that backup chart. So bridging of multiple network segments. The Omni link consists of segments joined by OAL intermediate nodes acting as bridges, as I showed in that earlier diagram. Some examples of what these blue, red, and yellow networks would be. In civil aviation, we have these multiple providers, including ARINC, CETA, Inmarsat, and others. Another example might be bridging network segments within an enterprise network. Another example might be bridging multiple enterprise networks like Boeing, Airbus, Lockheed, just to name a few names there. But an even more relevant example to this group is that this can be used to bridge the IPv4 and IPv6 internets. So we can say that the IPv6 transition would be satisfied by putting in Omni interfaces out there, and then we'd be able to run IPv6 everywhere, even though the network is not always all transitioned to IPv4. We just bridge between the IPv4 and IPv6 internets. And that's my last chart.
Okay, are there any comments?
If there are no comments, then I think Fred, I think you have some echo on your side.
I'm sorry. I'm not sending audio right now. Is it feeding back?
At least someone had echo. Don't worry about it, because you are on the next presentation as well, right?
Okay.
And you can take more questions on this one at the end as well, right?
Okay.
Super. Go ahead. Omni IPv6 ND message sizing.
IPv6 neighbor discovery message sizing, and again, this relates to Omni. Next chart, please. Again, we see our Omni interface here. Next chart. So IPv6 neighbor discovery messages such as RS, RA, NS, NA include options, and the IPv6 neighbor discovery message options in TLB format is defined in RFC 4861. So there's an 8-bit type and an 8-bit length field in front of the value. Next chart, please. So since IPv6 neighbor discovery message option length field encodes the length of the option in 8 octet units, that means that the maximum length IPv6 neighbor discovery option is 2040 octets. 255 times 8 equals 2040 octets. Omni sub-options that go inside of an Omni option are also TLBs, but they're expressed in 1 octet units, excluding the type and the length fields. Omni sub-options may include large objects like ASCII strings, fully qualified domain names, protocol messages, and others. And so the Omni sub-options need to be made to include the maximum allowed for a single Omni option, a single IPv6 neighbor discovery option. So for that reason, the draft now fixes the sub-option type field to 5 bits and length field to 11 bits instead of the former 8 plus 8. Next chart, please. So the Omni option is an IPv6 neighbor discovery option with 1 or more sub-options. So you see the Omni option there on the left. It has essentially a blank slate that you write sub-options into. And then the sub-option format is on the right there, where you have this 5-bit subtype, 11-bit sublength, and then the sub-option data. Sub-option types include PAD1, PAD-N, and several others. They're in the document. Now with the 11-bit sublength field, that means that each sub-option can include up to 2048 octets. But if that would cause the Omni option to exceed its total length, the information already processed in the Omni option is accepted and the final sub-option is ignored. Next chart. So since a single IPv6 neighbor discovery message may include multiple Omni options, all are going to be processed in the order of appearance, and the union of information is accepted. Large object fragmentation across multiple Omni options is not currently supported. It would be specified in the future if necessary, but at this point, it doesn't look like it's needed. But IPv6 neighbor discovery messages as large as the Omni interface MTU are permitted. 9180 bytes for an IPv6 neighbor discovery message with no IPv6 fragmentation per RFC 6980. That means that we can craft a large neighbor solicitation message as an Omni adaptation layer path maximum payload size probe if we can get it to generate a small neighbor advertisement reply in return. Next chart. So the way it works is that the Omni adaptation layer can craft a large NS probe by including Omni options with large PAD-Ns, then send the probe over an underlying interface without any fragmentation. If the OAL destination gets it, it quickly skips over the PAD-Ns and returns a small neighbor advertisement without padding, and that small neighbor advertisement is assured to traverse all paths in the reverse direction. This allows us to test the one-way path from the OAL source to the OAL destination across any concatenated underlying networks in the path. Individual probes are expendable, they don't interfere with data traffic, and single probe success may indicate the opportunity to increase the path maximum payload size. But we still need continuous probing to detect path MPS changes in case there's a change in the path. Next chart. And this is what it looks like. So the OAL source sends a large NS message on the left-hand side. It may or may not make it to the final destination. If it makes it, the final destination sends a small neighbor advertisement message in the reverse direction, and that's going to be assured to traverse all paths back to the original source. So that's how we do the one-way probing to get our maximum payload size larger for the OAL fragmentation. Next chart. And I think that's the end for that.
Yep. Any questions or follow-up for Fred?
I've made some pretty bold claims in the original presentation at first, including the fact that we can consider the IPv4 and IPv6 transition to be good if we adopt OMNI because we're already where we need to be. I would think some of those things might warrant some further discussion.
Any comments from the working group? Fred, I'm sorry to admit that we're having trouble seeing that there being any significant interest in this work here.
Well, if there is no more people in the queue, I think we'll see each other again on Thursday with the more regular working group session. So that's going to be 1600 to 1800 UTC. That's morning, West Coast US. And in the meantime, follow up on the mailing list with, if there's any interest in these drafts that have a chance of either finding other working groups to continue their work or be adopted here. But we need to see some active interest in the working group to pick any of them up. Alexander, do you want to say something?
Yeah, this is related to the polls that have been run in MeetEcho. I see there are 2 polls, but I don't know what are the questions. I see the results in the polls, but
I didn't. I forgot to put a draft in the poll. The first poll was just a test, and the second one was for the first draft we had today. I didn't run the polls for the other drafts, so we'll have to take that to the mailing list if there is interest to continue work or in this working group or in other places.
Okay.
Well, good. Unless there's some other topics, I think we are done for today. So we'll give you a little more time for your day, and see you at the next session.